this program, we'll look at how to solve navigational problems using two different types of flight computers. First, we'll discuss the Mechanical Slide Graphic, or CSG computer. Then we'll cover the TechStar, which is an electronic flight computer. Because this program is only an introduction, you should study the operator's manual for the computer you've selected in order to become thoroughly familiar with it. If you have a computer handy, you might want to work the problems as we're going through the program. We'll pause periodically to allow you to complete the problem. If you're only interested in the TechStar computer, you can forward the tape to that part of the program. The CSG computer has two sides, the wind side and the calculator side, which can be used to solve a variety of problems including time, speed, distance, fuel consumption, true airspeed, density, altitude, and conversions. There are three scales on this side of the computer. The outer, or A scale, can represent distance, fuel, speed, or other units, depending on the problem you're solving. The middle, or B scale, may represent similar items, as well as time in minutes. The inner, or C scale, is simply a conversion of time in minutes to time in hours and minutes. The outer scale is fixed, while the inner two scales are printed on a single rotating disc. The numbers on the computer can be assigned different values depending on the problem. For example, the 60 can have a value of 0.6, 6, 60, 600, and so forth. By mentally estimating the approximate answer, you can place the decimal point in the proper position. The graduations between the numbers, however, are not always equal. For example, between the 80 and 90, there are 10 divisions, with each division representing one unit. The third line right of 80 could be 8.3, 83, or even 830. Between the 21 and 22, there are only 5 divisions. Here, each line represents 2 units, so the third line right of 21 could be 21.6, 216, and so forth. Most of the calculations on the computer are ratios or fractions. For example, when determining time, speed, distance problems, there are 3 variables: elapsed time, speed, which is usually ground speed, and distance. If you know any 2 of the variables, you can quickly solve for the third. The face of the computer shows you how to solve for the unknown value in these ratio problems. If your aircraft speed appears over the index, you will find distance on the A scale and time on the B and C scales. For example, assume you're planning to fly your airplane at 140 knots for a distance of 350 nautical miles. How long will your flight take? First, place the speed index under 14, which is 140 knots, when you mentally delete the 0. Then look under the 3.5, or the distance of 350 nautical miles, to find the time in minutes. In this case, it is 150 minutes. Notice that you have to add a 0 to the 15. 150 minutes can be quickly converted to 2 hours 30 minutes by referring to the C, or hour scale. You can also use the computer to find the distance flown in a given period of time. For instance, at a ground speed of 120 knots, how far will you travel in 2.5 hours? First, set the speed index under the ground speed of 120 knots. Then go to the C scale and locate 2.5 hours or 150 minutes on the B scale. Directly above this number on the distance scale is your answer, 300 nautical miles. You determine the ground speed of your aircraft in a similar manner. If you've traveled 349 miles in 2 hours and 15 minutes, what is your ground speed? First, locate the time for this flight. Since 2 hours and 15 minutes is not marked on the C scale, you should use the time in minutes, 135, on the B scale. For 349 miles, you'll have to estimate the distance from the line representing 345 and the one showing 350. Then you can read your ground speed directly above the speed index mark. In this case, it is 2.5 lines right of the 1.5. By placing the decimal in the correct position, you can determine the ground speed to be 155 knots. Fuel consumption problems are basically the same type of calculations, except that the index now points to the fuel rate, which in this case is gallons per hour. The outer scale shows the amount of fuel burned, while the inner scales still show time. Suppose in your flight planning you need to know how much fuel you will need if your destination is 3 hours away and your airplane burns 8 gallons of fuel per hour. Like the speed problem, set the index mark under the rate of 8 gallons per hour. Then find 3 hours on the inner scale, or 180 minutes on the middle scale. Read the fuel required, 24 gallons, directly above this time. Another type of fuel problem is to determine your endurance, or how much time you can stay aloft. Assume your airplane has 42 gallons of fuel on board, and it uses 11 gallons of fuel per hour. This time, set the index under 11, which is the rate per hour. Under the 42, read 229 minutes, or 3 hours 49 minutes on the inner scale. You can also use this side of the computer to determine true airspeed. However, to do this, you must know 3 things: calibrated airspeed, pressure altitude, and air temperature. While in the air, you can determine the temperature by referring to your outside air temperature gauge. For pre-flight planning purposes, you can get the forecast temperature for your planned altitude from the winds and temperatures aloft forecast. If you're unsure of the pressure altitude and you're in an airplane, you can determine it by setting the altimeter to 29.92 and reading the indication. Make sure you reset the altimeter back to the current reported setting when you're finished. Calibrated airspeed can be found by referring to the pilot's operating handbook. Once you've determined all the necessary variables, use the window marked for true airspeed and density altitude and align the temperature in degrees Celsius over the pressure altitude. Then read the true airspeed on the A scale opposite the calibrated airspeed on the B scale. As a sample problem, suppose the pressure altitude is 5,000 feet, the temperature is 20 degrees Celsius, and your calibrated airspeed is 150 knots. Using the proper window, align +20 opposite the 5. Notice that the altitude scale is in thousands of feet and plus temperatures are to the left of 0. Next, find the calibrated airspeed of 150 knots on the B scale. Then read the true airspeed of 166 knots on the A scale. Density altitude can then be read directly from the center window. If the conditions remain the same as in the previous problem, the density altitude will be approximately 6,700 feet. The other window is used to compute true altitude. Instructions are listed near the window. The computer can also be used for conversions. For example, a temperature conversion scale is located at the bottom of the disk. For nautical statute mile conversions, 2 arrows at the top of the fixed scale give the proper relationship. These and many other conversions are covered in your owner's manual. The wind side of the computer is used to determine how the wind is affecting your airplane's ground track and speed. As you learned earlier, the moment an object becomes airborne, it is affected by the wind. If the object has no propulsion of its own, such as this balloon, it will float at the same speed and in the same direction as the wind. An airplane is also influenced by the wind. While it doesn't drift freely like the balloon, it is deflected from its intended flight path and its ground speed is affected. To illustrate, suppose a free balloon is released in a 15-knot west wind. At the same time, an airplane begins a flight due north at 100 knots. After 1 hour, the balloon will have drifted 15 nautical miles to the east. The airplane, flying northward, also will have drifted this same distance. In this situation, you should have pointed the nose of the aircraft to the west of the destination to compensate for the wind drift. The angle formed between your heading and the flight path is called the wind correction angle. The wind side of the computer helps you determine to what extent you'll have to fly into the wind. There are two parts to this side of the computer: a rotating azimuth and a sliding grid. Notice that the grid is printed on both sides. The high-speed side is used mainly for solving problems at jet speeds. There is also a statute and nautical mile scale, which can be used on sectional and WAC charts. The low-speed side of the scale is used for aircraft flying at lower speeds. It contains concentric arcs, which represent speed, and straight lines radiating from a central point, which represent degrees right or left of the center line. The rotating azimuth is graduated into 360 degrees. The center of the azimuth is a frosted transparent material, which can be marked on with a pencil. Directly in the center is a round circle known as the grommet. At the top, on the fixed portion of the computer, is a true index, which is used as a reference for plotting wind and course direction. The center line printed on the grid can represent any direction by just rotating the azimuth so the desired degrees are aligned under the index. At the top of the grid are easy-to-follow instructions on how to find ground speed and true heading. To determine how wind affects your airplane, you will need to know true airspeed, wind direction and speed, and true course, which is your intended flight path as measured from the true North Pole. The method for determining true course will be explained in the next section. Suppose that you've determined your true course to be 310 degrees. The predicted wind at your altitude is forecast to be 180 degrees at 16 knots, and your true airspeed is 120 knots. What heading will you have to fly to maintain your desired course, and what effect will the wind have on your ground speed? The first thing you must do is plot the predicted wind by rotating the azimuth until the wind direction is under the index. Next, slide the grid until the grommet is over one of the heavy speed arcs. In this example, let's use the 100-knot arc. Then count up from the grommet 16 knots and make a mark, which we'll call the wind dot, over the center line. The wind speed should always be plotted up from the grommet. Now rotate the azimuth until the true course of 310 degrees is under the true index. Then slide the grid until the wind dot is over the true airspeed of 120 knots. Your ground speed can now be read under the grommet. In this case, it is 129 knots. You can then determine the wind correction angle by counting the number of degrees the wind dot is located from the center line. In this case, each line represents 2 degrees, so the wind correction angle is 6 degrees left. Since the correction is to the left, you must subtract 6 degrees from the true course to obtain your true heading of 304 degrees. To verify that these figures are correct, you can visualize that the grommet represents your airplane and it's heading toward the index mark. Since the wind is behind and to your left, ground speed should be higher than true airspeed, and the true heading should be left of the true course. This concludes the coverage of the CSG computer. If you wish to learn how to operate a Techstar computer, let the tape continue. Otherwise, please forward to the next section on pilotage and dead reckoning. The Techstar electronic navigation computer is quick, accurate, simple to operate, and is designed to solve today's navigational problems. Like the different sides of a mechanical computer, the Techstar has various modes which you must use, depending on the type of problem you're solving. The time, speed, distance mode is used for determining, among other things, how far you can go,
how long it will take to get there, and how much fuel you will need. The altitude airspeed mode can be used to determine density, altitude, and true airspeed. The wind mode is used to find your heading and ground speed. The weight and balance mode is used for determining gross weight, center of gravity, weight shifts, and percent of mean aerodynamic chord. The timer mode helps you compute departure, en route, and arrival times, convert different time formats, and acts as a time up or time down counter. To access the different modes, after you've turned on the computer, simply press the Mode key. This displays the 5 areas. To go into any one of the modes, press the Line Parameter key. Let's begin with a Time Speed Distance, or TSD problem. Once you're in a mode, the Techstar computer indicates which mode you're in and displays the variables you'll need to solve a problem. Notice that on this menu, the variables needed to solve a fuel problem are also displayed. Most of the calculations done on the computer are ratios or fractions. For example, when calculating time, speed, or distance, there are 3 variables: elapsed time, speed, which is usually ground speed, and distance. If you know any 2 of the variables, you can quickly solve for the 3rd. Suppose in your pre-flight planning, you want to find out how long it will take to fly 350 nautical miles if your airplane averages 140 knots. The first thing you must do is tell the computer which variable you want to solve for. In this example, you're solving for time. Now key in the distance of 350 nautical miles, which is displayed on the scratch pad at the bottom of the screen, and then transfer it to the appropriate parameter line. Next, enter the ground speed of 140 knots by keying in 140 and then pressing the ground speed parameter line key. If you had wanted to, you could have entered the ground speed before the distance. Known variables can be entered in any order. You are now ready to find the time by pressing the compute key labeled CMP. The answer is 2 hours, 30 minutes. Now suppose you've arrived at your destination and it only took you 2 hours and 20 minutes. What was your actual ground speed? The first thing you'll need to do is select speed as the variable you're solving for. Since the distance didn't change, enter it into the distance parameter line. Key in the time by pressing the 2, and then the colon key followed by 20. Next, press the time parameter line key. Now find the actual ground speed by pressing the compute key. Your actual speed over the ground was 150 knots. Fuel problems can also be solved in this mode. For example, after you landed, you had your plane refueled and found out you had used 21 gallons of fuel. What was your actual rate of fuel consumed per hour? You could solve this problem using the secondary compute function of this computer, which will be discussed later. But for now, let's go back to the main menu by pressing the Mode key. Then access the Time Speed Distance mode and select the flow rate by pressing the key next to FLO. Next, enter the time of 2 hours, 20 minutes. Enter the fuel used by keying in 21 gallons and transferring it to the fuel quantity parameter line, labeled F. To find the fuel rate per hour, press the compute key. The answer is 9 gallons per hour. Now let's go back to the screen where we solved for ground speed and see how this same problem can be solved using the secondary compute function. To determine fuel rate from this point, simply press the compute key a second time. This gets you to an extended output screen where additional parameters may be computed from the same variables. Then key in 21, which was the total fuel used, and transfer it to the fuel parameter line. Fuel flow can be determined by pressing the compute key again and then the flow parameter line key. The answer is the same, 9 gallons per hour. Use of the secondary compute function is further explained in the operator's manual. To determine true airspeed and density altitude, you must be in the altitude airspeed mode, which is indicated by an ALT-AS in the display. To determine true airspeed, you must know three things: calibrated airspeed, pressure altitude, and air temperature. Calibrated airspeed, which is indicated airspeed corrected for installation and instrument errors, can be found by referring to the airspeed calibration table in the pilot's operating handbook. While in the air, you can determine air temperature from the outside air temperature gauge. For pre-flight planning purposes, you can get the forecast temperature for your planned flight altitude from the winds and temperatures aloft forecast. The pressure altitude can be found, if you're in the airplane, by setting the altimeter to 29.92. However, when you've finished reading the indication, make sure you reset the altimeter back to the current reported setting. As a sample problem, let's determine true airspeed, or TAS. Assume the pressure altitude is 5,000 feet. The calibrated airspeed is 150 knots, and the temperature, which was determined from a winds and temperatures aloft forecast, is 20 degrees Celsius. First enter 5,000 feet into the pressure altitude parameter line, labeled PA. Next, enter the calibrated airspeed and the temperature. Since the temperature was determined from a forecast, we need to input the temperature into the true temperature parameter line. Had we obtained the temperature while in flight from the outside temperature gauge, this value would have been entered in the indicated temperature line. Notice that once you've entered a value into one of the OR variables, meaning the value can go into either line, dashes appear in the line next to the other variable. Now press the compute key. The true airspeed, in this example, is 166 knots. Density altitude is also determined in this mode. If the conditions remain the same as they were in the last example, all you have to do is press the compute key a second time. The answer is 6,712 feet. The wind mode of the computer is entered by pressing the wind key. When you're in this mode, the word wind will appear at the top of the display. When an object leaves the ground, it is affected by the wind. If an object has no propulsion of its own, such as this balloon, it will drift in the same direction and at the same speed as the wind. An airplane is also influenced by the wind. While it doesn't drift freely like the balloon, it is deflected from its intended flight path and its ground speed is affected. To illustrate, suppose a free balloon is released in a 15-knot west wind. At the same time, an airplane begins a flight due north at 100 knots. After 1 hour, the balloon will have drifted 15 nautical miles to the east. The airplane, flying northward, will also have drifted this same amount. In this situation, you should have pointed the nose of the aircraft to the west of the destination to compensate for the wind drift. The angle formed between your heading and the flight path is called the wind correction angle. To determine how the wind is affecting your airplane, you need to know 3 items: true airspeed, wind direction and speed, and true course. True course is your intended flight path as measured from the true North Pole. How this course is determined will be covered in pilotage and dead reckoning. Suppose you've determined your true course is 310 degrees and the predicted wind at your proposed altitude is out of the south, or 180 degrees, at 16 knots. Your true airspeed is 120 knots. What heading must you maintain to fly your desired ground track? And what effect will the wind have on your ground speed? After verifying that you're in the wind mode, press the parameter line key representing the variable you want to solve for. In this case, it's heading. Now enter the true airspeed of 120 knots into the true airspeed parameter line. Next, enter the wind direction of 180 degrees into the wind direction parameter line, labeled WDR. The wind speed of 16 knots is entered next by keying in 16 and pressing the WSP line parameter key. The true course of 310 degrees can then be entered into the course, or CRS, parameter line. Your true heading is determined by pressing the compute key. In this case, you must fly 6 degrees left, or 304 degrees, to maintain a ground track of 310 degrees. Notice your ground speed, or estimated speed over the ground, is also given. In this case, it is 130 knots. If you want to find the precise speed, just press the recall key labeled RCL and the ground speed parameter line key. The precise ground speed then appears in the scratch pad. In this case, it's 129.657 knots. To verify that the wind correction and ground speed figures are correct, you might want to visualize the airplane flying on a true course of 310 degrees with the wind coming out of the south. Since the wind is behind and to the left of the airplane, ground speed should be higher than true airspeed, and the true heading should be left of the course. Now let's do a sample weight and balance problem where we solve for center of gravity. In this problem, the basic empty weight of the aircraft is 1,467 pounds, and its moment is 57,300 pound-inches. The total weight of the pilot and front seat passenger is 340 pounds, and the front seats are located 37 inches aft of the datum. The combined weight of the rear seat passengers is 280 pounds. The rear seat is located at station 73. There are 40 gallons of fuel on board. The tanks have an arm of 48 inches. There is also 20 pounds of luggage located 95 inches aft of the datum. To solve this problem using the TechStar, just follow the prompts. Input the weight and moment or arm for the first set of figures, which for this problem is the basic empty weight. Notice that when you entered the moment, dashes appeared in the arm line. The RF parameter line can be used if you wish to use a reduction factor. After you've entered the information for the first item, you'll need to press the Next key. This brings up the menu for the second set of values, which is the weight of the front seat occupants. When you press the Next key after entering an arm value, the moment appears for approximately 3 seconds before the screen goes to the next set of values. Continue entering the information for the rear seat passengers. The fuel. And the baggage. Once you've entered all values, press the Compute key. In this example, the total weight is 2,347 pounds. The total moment is 103,740, and the center of gravity is 44.2. Now that you've worked individual problems on the TechStar, let's work a multi-part problem similar to one you might find in your pre-flight planning for a cross-country flight. You've determined you're going to be flying at a pressure altitude of 3,500 feet and the temperature at the proposed altitude is 68 degrees Fahrenheit. Your airplane cruises at a calibrated airspeed of 120 knots, and the wind at altitude is predicted to be 095 degrees at 16 knots. The true course to your destination is 032 degrees, and the distance is 320 nautical miles. For fuel planning purposes, your airplane uses 9 gallons of fuel per hour. What you need to determine is the true airspeed, which will then allow you to find your heading and ground speed. Once ground speed is determined, you'll be able to calculate the time and route to your destination and the amount of fuel needed for the trip. The first item you must determine is true airspeed. You do this by entering the altitude airspeed mode, identifying what you are solving for, and then keying in the pressure altitude and entering it into the pressure altitude parameter line. Next, enter the temperature. Since this value must be in degrees Celsius, you must convert 68 degrees Fahrenheit to degrees Celsius. You can do this by pressing the weather conversion key. Then transfer the value in the scratch pad to the degrees Fahrenheit parameter line and compute for degrees Celsius. The result is 20 degrees. In order to transfer this to the original problem, you must press the recall key, then the degrees Celsius parameter line key. This moves the converted temperature down to the scratch pad. Now you can move this value to the original problem by pressing the mode key and the temperature parameter line key. The calibrated airspeed is the last item to enter in this mode. Now press the compute key. In this case, true airspeed is 129 knots. Since you'll need the true airspeed value to determine heading and ground speed, you must transfer this number to the wind mode. Notice that when you move the true airspeed to the scratch pad, the exact value of the true airspeed is displayed. To access the wind mode, press the mode key followed by the wind parameter line key. Once you're in the wind mode, indicate what you want to solve for. In this problem, it's heading. Then transfer the true airspeed value to the true airspeed parameter line. Next, key in the wind direction, wind speed, and true course. You're now ready to determine your heading by pressing the compute key. Since your course is 032 degrees, you must fly 6 degrees right, or 038 degrees to track the desired course. Also notice that your estimated ground speed is 121 knots. Now that you know your ground speed, you can find the time and route to your destination. To do this, press the recall key followed by the ground speed parameter line key. You can now transfer this value to the time speed distance mode by pressing the mode key followed by the TSD parameter line key. Since you're solving for en route time, press the time or TIM parameter line key and transfer the ground speed to the speed parameter line. Then key in the distance of 320 nautical miles and enter it in the distance parameter line. Time en route can now be computed. The answer is 2 hours, 38 minutes, 48 seconds. To determine the amount of fuel required, press the compute key a second time and enter 9 gallons per hour, which is the fuel rate, into the fuel flow parameter line. The time is still in memory, so all you have to do is compute for total fuel. The answer is 23.8 gallons. The regulations state that for any VFR flight during the day, you must add at least a 30-minute fuel reserve. The easiest way to do this is to place the fuel for the trip into one of 6 user memories. You can do this by moving 23.8 to the scratch pad, then storing it by pressing the store key, labeled STO, followed by one of the first 6 arithmetic keys. Then replace the time en route with the 30-minute reserve. Now compute the fuel required for the reserve, which is 4.5 gallons. Adding this figure to the fuel en route, which you can retrieve by pressing the recall key and the appropriate arithmetic key, means you must have a little over 28 gallons of fuel on board the airplane before you make the trip. Using the Techstar computer will enable you to solve navigational problems encountered by a pilot. By becoming thoroughly familiar with it, your workload during pre-flight planning and in-flight computations will be greatly reduced.